Hello and welcome to another operations research video. This chapter, we're talking about decision analysis. Essentially, how do we make decisions based off of incomplete information? And so we're going to start off with a motivating example, and then we'll talk about a couple of criteria that you can use to make decisions. And then we'll kind of go deep in some of the other videos on expounding on kind of how we layer on that decision-making process. So we've got a computer chip company that developed a new computer chip. They have to make a decision, and they've got two alternatives, and I'll kind of highlight them in this table down here. They've got two what we call alternatives. These are the choices that they can make. They can either build the computers based off of those chips, or they can sell the rights to the chips to someone else. Okay. If they sell the rights to the chips, they get 15 million from the sale of those rights. But if they choose to build computers, they're taking on some risk. Okay, and so this whole section is about kind of risk reward and balancing those. So if they build the computers, they're going to have some setup costs of 6 million. And they're pretty sure that they can sell at least 10,000 computers at 600 in profit each to make back that initial investment. So the worst they can do is get 0 million and break even if they only sell 10,000 computers. But they think there's a 40% chance that the computer catches on and goes kind of broader in the market, and then they're able to sell 10,000 computers or 100,000 computers, 10 times as many computers at that same profit margin minus the 6 million setup. They'd expect to get 54 million as a result. Okay, and so if they choose to build the computers, there's sort of a risk reward. Either they get nothing or they get 54 million, depending on the market rollout. And so these two possibilities for the market rollout, those are what are called states of nature. They don't have direct control over how many they'll sell, right? They'll do their best job to kind of market them, but there's some element of chance. There's some chance that they'll only sell 10,000, and there's some chance that they'll sell 100,000. That chance of status, and that's this last row in the table, represent the probability of a 60% chance that they only sell 10,000 and a 40% chance that they go broader and sell 100,000. These are what are called prior probabilities. They represent the company's best estimates on the likelihood of each of the states of nature. And then in the middle of this table, the dollar amounts here, those are what are called the payoffs or the payoff matrix. Okay, and essentially for each of the alternatives, it tells you what the expected value to the company is, right? And so we use value loosely. Oftentimes it's in terms of profit, but it wouldn't have to be in terms of profit. It could be some other value that the company gets. Okay, and so a typical decision analysis looks like this. I will say this is maybe a simplified example. You could have more than just two states of nature. You could also have more than two alternatives. Here we're thinking about discrete states of nature. So it's either this or that. In practice, you could have a continuous state of nature where we expect to sell somewhere between 10,000 and 100,000, and then you'd have to have a continuous probability distribution in that case. We won't go that deep, but there's definitely more you can build off of this. I will say this chapter is a little bit heavy on the probability, but it's mostly focusing on the discrete probability. So your textbook has an extra online chapter on probability, and I've suggested a couple of the sections of that to kind of be a refresher on probability theory. But we'll also explain all the probability important bits that we meet along the way. So that's sort of an overview of the terminology of a problem, as well as kind of a motivating example that we'll use to evaluate different decision criteria. So we're going to meet 3 decision criteria. The first decision criteria is the max and min criteria. Okay. This criteria takes the viewpoint that your states of nature are sort of determined by a malevolent opponent that's trying its best to minimize your gain, right? And so what you want to do is for each of the alternatives, so our alternatives are build or sell, what you want to find is the min payoff for each of those. Okay, and so if we choose build, the payoffs are either 0 or 54 million. The minimum of those two is 0 million. And if we sell, the 2 payoffs are 15 million and 15 million. The minimum of 2 identical numbers is just the 15 million. Okay, and so for each criteria, we find the minimum payoff. So really the minimum of that row of the payoff matrix. We're just finding the minimum of each of those rows. And then once we've found the minimum payoff, we then choose the alternative that gives us the best minimum payoff. And so in this case, the max and min criteria says that we should sell. Okay, and this is sort of our best guarantee, right? Our best worst case is another way to put it. And if you're very conservative in your decision making, this is really the most conservative decision criterion that you can use. You can't do worse than 15 million if you choose to sell, and that's the best guarantee that you can have. Okay. Whereas if you choose to build, you might get nothing. And then if you think of maybe all the sunk cost in the research, 0 million might actually be pretty bad for your company, and it might not represent actually breaking even. Maybe some critique of the max and min criteria is that it is overly conservative. Usually we think of those states of nature of how much you sell as being kind of random and maybe neutral would be a better way to think about them, is that they don't care which choice you made. Kind of the states of nature, we sort of think of them, at least in the modeling perspective, as a roll of the dice. Okay. And in that sense, this might be overly conservative in that it sort of takes the opinion that nature's out to get you. Okay. And that's really the case. And we can kind of maybe give up on what could be a very high payoff to build because we don't want the downside risk. And sometimes that downside risk is relatively rare. In this case, the downside risk on build was 60%. And so it's pretty decently likely that we will just break even on the build alternative. But sometimes that bad alternative is very rare, and we avoid an alternative just because it has one rare bad state of nature. So that's something to keep in mind. Okay. Let's move on to the next decision criteria. The next decision criteria is the maximum likelihood criteria. Maybe one other thing we could say about the max and min is that it ignores the likelihood of each of the states of nature. It just says what's the worst possible outcome. The maximum likelihood starts to take that into account. Okay, and so what we do is we identify the most likely state of nature, and then we look at the payoffs for that most likely state of nature. We ignore all other states of nature. And so in this case, we'll look at most likely. And if we look back at our prior probabilities, we had a prior probability of 0.6 or 60% for only selling 10,000. And we had a prior probability of 40%. 60% is more likely than 40%. And so we're going to say that cell 10,000 is our most likely state. And then we look at each of our alternatives, either build or sell. And under the most likely state, build will give us a payoff of 0 million and sell will give us a payoff of 15 million. So in this case, I'm just taking the column from underneath the cell 10K. And in this case, then we again choose the decision or alternative with the maximum payoff in the most likely state. And so max likelihood in this case tells us that we should also sell. Okay, because the most likely state is that we only sell 10,000 computers. And so looking only at that most likely state, we should sell. Okay, some kind of pros of this approach is that sometimes the prior probabilities, the 60% and 40% that we see there, are a little bit kind of subjective. Well, they're always subjective, I'll say. I'll kind of assert. They might be based on past experience, which gives them maybe some basis, but still it's always an assumption that the past will play out in the future, even if you do have them based off of past experience. So those prior probabilities can be subjective, and instead of worrying so much about their value, all you need to decide on is which is more likely. Okay, and that simplifies maybe the setup and the thinking through of your states of nature. You don't have to assign a specific probability to each state of nature, but rather you can just decide which is the most likely, and then choose the alternative that does best under the most likely state. Okay. The con to this, though, is that you ignore all other states of nature. And so you ignore a lot of relevant information in the decision-making process. In this case, our two states of nature are fairly equally likely, not perfectly equally likely, but pretty close to being equally likely. And so, yeah, the 40% chance of selling 100,000 is still very likely, and we've sort of ignored that possibility completely. If we do this, we sort of ignore what might be rare risks in some states. So some states of nature might be rare, but they might present very large payoffs or risks. And if we only look at the most likely state, we ignore those maybe extreme risks or extreme rewards that might be unlikely or not as likely, but still possible and maybe even still probable. Okay. And so that's maybe the critique of maximum likelihood. It is simpler to implement, to think through and set up, but it maybe ignores some very important information from the other states of nature. Okay. The third criteria that we'll actually focus on mostly is what's called Bayes decision criteria. And Bayes decision criteria focuses on a concept called expected value. And the idea is that we need to use the best available estimates of the probabilities. Those are the prior probabilities. And we want to calculate the expected value for each possible decision alternative. Okay. And so here I'm going to write expected value, and kind of the formula for expected value is the sum over all states. So maybe I'll just write sum over states, states of nature. The probability of that state times the payoff of that state. So that's the formula. And let's see what it looks like for build and for sell. So for build, we're going to take the probability of the first state. The first state is that we sell 10,000. So the probability of the first state is 0.6. And then we're going to multiply that by the payoff for the first state. And for build, the payoff for the first state is 0 million. And then we're going to add to it now the probability. Now we kind of move through each of the states. The probability of the second state, which is 40%, times the payoff from that second state, which is 54 million. Okay. And if we go ahead and crunch the numbers, do the multiplication and add them together, we should end up with a payoff of 21.6 million. Okay. If we repeat it for sell, we take the probability of selling 10,000 times the payoff when we sell 10,000, which is 15 million, plus the probability of selling 100,000 times the payoff for 100,000, which is also 15 million. And not surprisingly, our expected value if we sell, since the payoff in both states of nature is 15 million, is also 15 million. You can think of this expected value as a weighted average, where it's weighted by those prior probabilities. I'll maybe emphasize something here, is that these first two numbers, so this probability times this payoff and this probability times that payoff, those are representing the state of nature for sell 10,000. And then if we look at these two probabilities and payoffs, those represent the probability and the payoff in each of the alternatives if we were to sell 100,000. Okay. And so in this case, on average, that's what we kind of mean when we compute an expected value. On average, we should expect to get more out of building the computers than selling the rights. And so according to Bayes' decision criteria, Bayes says build. Okay, so the big advantage of Bayes' decision criteria is that it incorporates all available information, really all the information that we could hope to have. The kind of critiques of Bayes' decision analysis is that maybe these prior probabilities are a bit subjective, and we can think about, well, how does the answer change if these prior probabilities were to change? And so in the next video, we'll look at a little bit of sensitivity analysis on Bayes' decision criteria. Maybe another critique of Bayes' decision criteria is that this is an expected value, which you can think of as a long run average if we were to repeat this process. Now, when you make a decision, especially like a decision like this, you're probably only making that decision once. And so you're either going to get 0 or 54 million. You're not going to get this average value of 21.6. So it's only really in cases where you're making many similar decisions that you should expect to sort of realize the average value. So this is maybe true of the books example where they're drilling for oil, and maybe if there's lots of different oil wells that they're sort of making these decisions on, then they should sort of, on the average over all the oil wells that they're considering, they might realize that average value. But when you only make one decision, you're not realizing the average. You're getting one or the other of the payoffs. Okay. But you might think, well, if we as a company make a bunch of decisions, right? On average, like sort of we'll kind of break even on all those, or sort of Bayes' decision is still probably the best criteria given the data that you have. Okay. So kind of summarizing kind of the three decision criteria. Maximin chooses the worst payoff for each alternative and then chooses the alternative that has the best worst payoff. Maximum likelihood only looks at the state that is most likely and chooses the best alternative. Then Bayes' decision criteria computes the expected value of each alternative using those prior probabilities. Okay, and for the rest of this chapter, we're certainly going to build off of Bayes' decision criteria and go deeper into making decisions using Bayes' rule. Okay, so that's it for this video. The next one, we'll talk a little bit about sensitivity analysis.